Welcome to this last module of solid state physics, in which we will be doing magnetism and superconductivity back to back. And because the whole of solid state physics is merged into 1 week or one module, so we will have to be quick and only will give you the bare minimum description of both magnetism and superconductivity. But nevertheless, these are very important topics and one should learn it more rigorously than what will be presented in this course. We will try to give you a bird's eye view and you can build up upon that. So, we start with magnetism and we talk about different types of magnetic ordering which you all are familiar with, and in particular we will talk about dia, para and ferromagnets. There are also antiferromagnets and ferrimagnets, and so all those things we will not talk about here. So, we will give examples of magnetic materials, and main part of this discussion will form out of these elementary treatises of magnetic ordering, which means that we will talk about dia, para and ferromagnets to the extent we can in this course. So, starting with a bit of history of the magnetic phenomena. The magnetic phenomena was discovered long time back in lodestones, and the lodestone is actually a naturally magnetized piece of mineral. It is a magnetite, rather a iron oxide, which is one of the main iron ores, and you see the picture that it actually catches a lot of nails there. It attracts and holds all these nails there. The Greek philosophers have discussed magnetism between 625 before Christ to about 545 before Christ, and the ancient Indian medical text Sushruta Samhita, it also has mention about usage of these magnetites in removing metallic objects embedded in a person's body. And in ancient China, the earliest mention of a lodestone attracting a needle is found in the 1st century work there. So, the different types of magnetism that we are going to talk about here is diamagnetism. Diamagnetism is the tendency of a material to oppose an applied field, magnetic field, and therefore, it is repelled by a magnetic field, or rather the ordering takes place in a direction which is opposite to the field, and diamagnetic materials have no unpaired electrons, and this puts them in direct contrast with paramagnetism, where there are a lot of unpaired electrons there, and this paramagnetic material may not have a magnetization of their own, but when it is put in a magnetic field they develop magnetic moments. And ferromagnetic materials, they possess intrinsic magnetic moments, and they tend to align parallel to the applied field and enhance the external field in the way it has also unpaired electrons. And this picture that you see there is a schematic picture. All these green dots are the particles carrying the spin, like the electrons. At h equal to 0, you have these as neutral particles, they do not do anything. If you put a h pointing in the rightward direction, then the magnetization develops in the leftward direction as shown. Paramagnet in no magnetic field, that is h equal to 0. So, here we denote the magnetic field intensity or the magnetic field by h, and when you put them in a magnetic field, there is development of the magnetic moment along the direction of the field. So, these are paramagnetic materials, and as said earlier that they have a lot of unpaired electrons, and same goes with ferromagnetic material. In the absence of a field, they have the magnetic moment pointing in a certain direction. If you expose them to an external field, then of course, the magnetization takes place in a direction of the external field. This is a periodic table that is known to everybody, and we are simply showing the different magnetic elements there. So, the red are the antiferromagnetic elements, which are chromium, as you can see here. There are a lot of diamagnetic materials which are copper, zinc, silver, cadmium and so on, which are here in this region. Let me use a color maybe. So, this is in this region and so on, and then of course, there are a lot of them here, and that is the diamagnetic materials, and we have ferromagnetic. These are the well known ferromagnets, that is iron, cobalt, nickel, and also gadolinium here. These are well known ferromagnet with large sort of magnetic susceptibility. We will just talk about that in a while. And there are paramagnetic materials, which means they do not have a magnetic property of their own, but they show magnetism when they are exposed to external magnetic fields. And these are these pink colors like aluminum that you see here, oxygen, samarium, neodymium, Tc and uranium and all that, and then something that is here. They are also paramagnetic, and these are the rest of them which are shown here by a dull yellow color, that those are all non-magnetic materials. All right. So, we will sort of go to discuss some quantitative aspects of this magnetism, and we start with the molar susceptibility. So, we define magnetization M, which we have defined earlier, that these magnetization appears in a magnetic material when there is an applied magnetic field, and we write these linear relations. These are called linear magnets, because M is proportional to single power of H. There could be a non-linearity there at large fields, but we do not talk about them here. And these M equal to kappa H, and these molar susceptibility chi m is defined as this kappa into V m, where V m is the molar volume and it is equal to kappa into m over rho. M is the molar mass and mass density and so on and so forth. So, these are the quantitative way of describing a magnetic system. Very large number of elements are presented here, and you see that there are these ferromagnets which are here, and there are these nickel is a ferromagnet, manganese is also a ferromagnet and so on, and there are a varied degree of this values of chi m expressed in 10 to the power minus 6 centimeter cube per mole. And this sort of tells you that essentially gives you the same information that the periodic table gives, and here these values are presented, numerical values are presented. Okay. So let us see what how we can understand magnetism, and we will, as said earlier, that we will try to do it in the simplest way, or without doing too much of calculations, because this magnetism is a topic by its own which could take even one full course, and these applications of magnets etc., which we do not do it here. So, we start by saying that there are certain properties such as metallicity etc., which we know the metals can be explained within the framework of independent electron approximation. For example, a tight binding model. A tight binding model means that we are really talking about the band theory, that is when an electron passes through a periodic or a crystalline solid, there are gaps that form in the spectrum, and the wave function is of course given by what are known as the Bloch equations or Bloch theorem. But the energies, to get the energies in such periodic system or exact form of these energies in certain crystal lattices, one needs to resort to certain approximation, and one of them is tight binding approximation, which says that the electron while moving through the the periodic solid, it gets tightly bound to the ionic cores or the ionic locations, and the wave function only has a very small overlap with the neighboring ions, and it does not extend beyond that in the lowest order approximation. So, this is called as the tight binding model, and with this we can conceptually understand the energy spectrum, these resulting from an effective potential. We have also looked at phonons, how phonons are described as the quantized lattice vibrations. However, the magnetic phenomena, which specifically ferromagnetism and antiferromagnetism, they cannot be explained within this independent electron picture or the single particle picture. And many electron aspects, which means the interaction between the electrons, that they become important, and you can't describe these magnetic ordering such as ferromagnets and antiferromagnets without invoking the electron-electron interaction. And this ferromagnetism in 3D metals, these are specific examples such as iron, cobalt and nickel. They are caused by exchange interaction between the largely delocalized 3D electrons. Okay. However, some the lanthanide series, which are 4F transition metals, they require more localized description. These are ferromagnets, and they require, as we have said, that the interacting description. And so, explaining antiferromagnetic arrangement of spins also requires one to invoke the exchange interaction between the spin. So, the spins are they interact, the neighboring spins interact via localized interaction. However, the actual interaction is not between the magnetic moments, it is actually between the electrons. The Coulomb interaction is responsible for inducing these exchange interaction between the spins. So, we start with elementary treatise of diamagnetism and paramagnetism. So, these are magnetic ordering present in electrical insulators. Insulators means that they do not have any charge conduction properties. So, they are electrically neutral, and we need to study diamagnetism and paramagnetism in them. So, they can be largely understood, as I said, that by using independent electron approximation. However, for ferromagnets and antiferromagnets, we have to go beyond that and invoke electron-electron interaction. Okay. So, to start doing that, let us calculate the atomic susceptibilities. And how do we do that? Let us start with this kinetic energy operator, which takes a form in presence of a magnetic field, where the momentum is replaced by this term E A, where E is the electronic charge and A is the vector potential, and this vector potential is defined by the magnetic field into curl A. It is true that we have talked about magnetic field as H, and now we are talking about B, but they really mean the same thing. Here we have of course talked about H, and so if you really stick to H, let us not try to write this equation, but the A is the vector potential, and the magnetic induction vector has a relation, which is what we have written there. And one can fix a gauge, and usually it is more sensible to talk about a symmetric gauge. Symmetric gauge means if H is in the Z direction, A will have components both in the X and Y direction. That is called a symmetric gauge. And symmetric gauge for a constant H is represented by this half R cross H, where R and H and I, all of them are vectors. And what we do is that we put in this equation, equation number 2, we put this AI there, and what we get is that we get this resultant equation, and in which case we can solve it, or rather we can expand this square and get this term, which is Ri Pi dot Ri cross H and Ri cross H dot Pi. These are the cross terms. This is the 0th order term Pi square, and this is coming because of the magnetic field being present there. Okay. So, now you see that we can choose actually a gauge in which we can combine these two terms and really can write it like a single term, and that gauge is divergence if A equal to 0. So, you may actually want to work out this term, which is not difficult. And what we have finally is that we have these T0, which is nothing but pi square over 2m, which is the kinetic energy of the electrons without the magnetic field. This is the correction that is coming from this term that you see up there, and then these cross terms are put in here, where now we can use a vector identity with A dot B cross C, which is P is A and R is B and H is C, and can use this identity to write this equation as Pi dot Ri cross H equal to H dot Ri cross Pi, and Ri cross Pi is nothing but L, which is the angular momentum or the orbital angular momentum. So, that is the total orbital angular momentum, and this is H dot L, and this is like there is a sum over I, of course, and there is a Li there. So, it is H dot L, it is a total angular momentum. And so, in absence of any interaction, the Hamiltonian can be written as T equal to T0, which is due to the non-interacting term, that is without any magnetic field, sorry, not non-interacting, it is without a magnetic field. And then you have a term like that, and then a H squared term coming from this term, the term that you see there. Okay, so, we can put a laser pointer here, it is because of this term that you see, a H squared term. Now, the whole idea is that you will use a perturbation theory with this as the the perturbation term, and in order to do that we have to necessarily use a second order perturbation theory, because we have a term which is in quadratic in H square, and there is a term which is linear in H. So, if you have to treat both these terms together, then there is no other way but to go into the second order, and we will do exactly that, and write this term as so there is a H0 here, and then there is H prime. So, these will be our H prime, and we will do a perturbation theory with that. So, this is your H prime. You can write S, which is large, so that is the total spin and the total orbital angular momentum, and then these are xi square and yi square are nothing but the coordinates of these individual atoms, or they are involved in the magnetism. I mean, these are the coordinates of those atoms. Then mu b is equal to EH over 2m, and so this has a value which is 5.58 10 to the power minus 8 electron volt per Gauss, and the Landry factor that you see here is approximately equal to 2. There is some correction to that, let us not worry about it now. So, the energy correction can be computed using a perturbation theory, and using the unperturbed states of this Hamiltonian, which is the Hamiltonian without the magnetic field, that is H0. And this the basics of perturbation theory, that you do not know what the eigenfunction of the total Hamiltonian is, and if you can identify a term which can be used as a perturbation because of its smallness, then you can use or rather employ the eigenfunctions of H0 to compute the correction in energy and even the correction in wave function. We just talk about correction in energy because that is what we need. And after that we can take this magnetization will be defined by the the derivative of the free energy with respect to H, the magnetic field H. So, it is del F del H. Now, here of course, we have written out scalar equation where m and h etcetera all are taken as scalar quantities. That is because you can't divide by a vector, take a derivative with respect to the vector. So, what you do is that you take the derivative with respect to the magnitude of h. So, the susceptibility is defined as del m del h. Now, it is very clear that you have a double derivative. So, this is actually a del 2 f del h 2, and so you need the free energy to survive up to a second order in H, and that is why you need to evaluate this H prime up to H square. This is magnetic field, remember that, and these other things that we talk about are these other H, you can make it a curly H if you wish, and this are nothing but the perturbation term in the Hamiltonian. All right. So, this is the formula for the second order perturbation theory, which involves an energy correction and then the terms that are written there. And you see that each term is of the order of h square, where h is a magnetic field, h square here because of the second order term. However, if you note that this we have used a first order perturbation theory. So, this is second order because we are interested in getting h square, and this is first order, and this is okay because we want delta E n up to second order in h square. Okay. So, we treated first term in up to second order and the second term up to first order. So, that our correction up to order h square is obtained. And why do we want h square is just what we have written here in equation 10. So, we need the free energy or the energy to be take a double derivative with respect to magnetic field. So, that we need these correction to be of the order of h square. And if you have all the if you really talk about an insulating material, then the total orbital and the spin angular momentum quantum number is 0, which means L equal to S equal to 0, total L S equal to 0. So, we have only corrections coming from the second term or the last term, and that will give us correction if you do it carefully. Then this you have to calculate this expectation value of this x I square plus y I square, which are nothing but the planar coordinates of these atoms. And in an isotropic crystal, your x square plus y square plus z square is equal to r square. So, if x, y and z are treated at the same footing, then x square plus y square is really 2/3 of r square, and that is what is written. You see a factor of 2/3 coming out, and that is you have to calculate the coordinate square of those the atoms which are involved in this process or in this calculation. So, this phi 0 is nothing but the ground state wave function. All right. So, we will calculate the susceptibility using this minus n by v and this del 2 del E 0, that is the correction to the ground state energy by h square. You have it's second order in h. So, you take a double derivative, and what you land up with is this expression, and this is of course an expression for the magnetic insulators, the diamagnetic susceptibility. Because of this negative sign, you see that there is a negative sign that indicates diamagnetism, and n is basically nothing but the small n is nothing but n over v, that is the number of or rather the density of these ions that are involved. So, this is an expression for the susceptibility, magnetic susceptibility that we get, and these are for the insulators. Now, we keep talking about these filled shell materials or the insulating materials, and so these equation let us see this equation is really, let us call this as equation. So, we want to actually refer to this equation 13. So, we will make this correction here, sorry about that. So, it is equation 13. So, electron in the outermost shells will contribute maximum because of the large mean square distance, because r I square is the mean square distance from some chosen origin. So, the origin is assumably in the nucleus or inside the atom, and you measure r I square with respect to the origin, and that can be obtained by so r I square is maximum. So, this contribution to this diamagnetic susceptibility is maximum for the ones that are in the outermost shell. So, we simply replace this sum or rather the expectation value by this r out square and multiplied by the number of the z out is like the atomic number, and so we simply replace this expectation value by these r I square, and that the Ri square would be maximum. So, that corresponds to the R out which are in the outermost shell, and then you have this expression which is the diamagnetic susceptibility, and these are, they correctly explain the magnetic behavior of these halides, alkali halides such as helium, neon, argon, krypton, xenon, etc. All right. So, let us now talk about partially filled shell materials, and we now do not have this Li sum over Li or sum over Si not equal to 0. So, Li is not equal to 0 and Si is not equal to 0 either. So, we have now n identical non-interacting spin particles in presence of an external magnetic field. The Zeeman term is represented by this minus mu b s dot h, and what we do is that we will follow a statistical route in order to calculate the partition function, and this partition function can be calculated for all orientation of s from minus s to plus s corresponding to this Zeeman Hamiltonian that is written up there, which is minus mu b s dot h. Now, we have made a distinction, this h is basically the Hamiltonian and this h is basically the magnetic field, and beta is equal to 1 over k T. So, this sum actually goes over 2 s plus 1 states from minus s to plus s and at a given temperature T, and so all these states are thermally excited at a temperature T with appreciable probability. So, one can calculate these partition function in a closed form, which will be obtained by summing up a GP series, and then you take this f is equal to minus k T log z, and then calculate m with this formula using minus del f del h, and one gets a Brillouin function which is nothing but this thing where x is equal to mu b h over k T. And this magnetization is obtained in terms of some spin, and spin is a general spin. You can put it s equal to half, but s is general, and this is the Brillouin function, and this Brillouin function, when you plot it for different s values, they look like this. The ones that is for smallest s, which is that blue curve which is outward, and the red one which is the largest spin that is considered here is the innermost curve. So, that is the just to show you how the Brillouin function look like as a function of x, where x is defined as mu b h by k T. So, let us look at various limits of this behavior of the either the magnetization or susceptibility. So, let us just talk about x much greater than 1, which means that the mu b h is much greater than k T. Okay. So, which means that this magnetic energy or the associated magnetic energy is much larger than the temperature, which means temperature is small. So, at low temperature the magnetization appears saturation value, because this B s which is this Brillouin function that tends to be 1, which is what you see here. So, that is the behavior for large x, and so that is your x large, and you get B s equal to 1. So, the saturation, the magnetization attains a saturation. In the other limit, when you have your the temperature is low, rather temperature is high, the magnetic energy is much lower compared to the temperature. We can do a small x expansion of this Brillouin function, which yields the Brillouin function to have a form which is s plus 1 divided by 3 s into x. That gives you what is known as the Curie susceptibility. So, when you put it back into this equation for the chi, which is nothing but, so the chi is defined as del m del h. So, then we have this m is equal to minus del f del h and chi is equal to del m del h. That acquires a form which is which goes as 1 over T for a spin s. So, this goes as 1 over T, and so remember that the susceptibility of these paramagnets which are for the electrons which are attached to atoms or ions, the susceptibility is Curie like, which goes as 1 over T, whereas there is another susceptibility which is what we are going to talk about just in a while. So, this is called as Curie's law. So, the susceptibility behaving inversely with temperature, and it is a feature of paramagnetic solid, all solids paramagnetic solids, and the law is found to be valid at large temperatures even when there is considerable magnetic interactions exist as well among the magnetic moments. The magnetic properties of the rare earth materials such as La, Lu, that is lanthanum, lutetium, neodymium, cerium, dysprosium, etc., they are adequately described by Curie's law. And I mean, in the next lecture means in the next slide actually. So, this is really the slide that you have. So, we will talk about Pauli paramagnetism, and also we will talk about diamagnetism. So, we have discussed Curie's law, and one should be aware at this moment that there is another type of paramagnetic phenomena that is applicable for metals, or where there are a lot of free electrons. These are called Pauli paramagnetism, and you can get a nice description of this in this book of statistical mechanics by Patria, and which obtains the magnetic susceptibility, which is called as chi Pauli. And the result is that that the chi Pauli is equal to mu b square into n, this the density of states at the Fermi level. There is another course of mine, statistical mechanics, where you would find the derivation of all these things. These are for free electrons, that is metallic susceptibility, or where there are a lot of free electrons. But the electrons that are bound to atoms, you get a Curie susceptibility, which is 1 over T. See, chi Pauli, that is Pauli susceptibility, is independent of temperature, only depends on the density of states at the Fermi level. Okay. So, they are distinct susceptibilities, one is Pauli, one is Curie. Now, to study ferromagnetism, it is shown by Heisenberg that for ferromagnetic ordering, or ferromagnetic ordering can be only explained if you invoke electronic interactions. Even though it has a structure of a spin-spin interaction in the Hamiltonian, the origin is purely electronic in nature, and an exact treatment of the interaction is not possible. It will be a long kind of derivation. Rather, if you are interested in some some exact solution for a 1D chain, spin chain, then again you can look at this statistical mechanics course. So, we will do quickly this mean field theory and skip all the rest of the things, but there are method of solutions of the Heisenberg model for a ferromagnet using these methods as well. So, coming to the mean field theory, let us try to see what the structure of the Hamiltonian is. And to begin with, let us start with a 2-spin system. It has just 2 spins, and there are 4 states, because there are these 2 spins, means 2 spin half particles. So, there are up and down particles, and one can actually form these up down, down up, and down down. Okay. And we can take a linear combination of that and can form these as S equal to 0 states, which are called as stinglet states, and these are the 3 triplet states formed out of up up, up down, plus down up, and down down. And these have certain properties, and if you just take a S square of the total S, basically is S1 plus S2 whole square, and then I can do a S1 square plus S2 square. Now, these S1 and S2 of course commute, that is why we can write that 2 S1 dot S2. Now, S1 square is for the spin half, it is S1 into S1 plus 1, and similarly for S2 square, it is S2 into S2 plus 1, both are 3 by 4 h cross square if you take S equal to half h cross. So, S square gives you a value which is this 3 by 2 h cross square plus 2 S1 dot S2, which means that if you operate it on its eigenfunction of S or S square, you get these as eigenvalue, and of course, you get an operator here whose eigenvalue you do not know, and this is interesting to us because these operator, we can now these operator S1 dot S2 has eigenvalue which is 3 by 4 h cross square or 1 by 4 h cross square, because this total S is equal to either 0 or 1. Okay. So, these are total S, this is actually the capital S. Okay. So, this for S equal to 0 is 0 and for S equal to 1 is 2 or 2 h cross square. So, we know the eigenvalues of these S1 dot S2 on for these singlet and triplet state, and we can now construct a spin only Hamiltonian, which are these Es is the energy of the singlet state and Et is the energy of the triplet state. This is a constant term, and then there is a term which is S1 dot S2. So, we can write down if we neglect this constant term in the Hamiltonian, we can write a Hamiltonian involving the two spins with a minus j term, which is the coupling between the two spins, and this case is nothing but Es minus Et, which is the difference between the singlet and the triplet energies. So, for a chain comprising of n spins and interacting via nearest neighbor interaction, we can write this Hamiltonian as minus j Si dot Si plus delta, which is similar looking to S1 dot S2, but now generalized to n spins. How can we do a mean field theory? We can do a sort of decoupling of the spins, so that each spin is an effective field due to the presence of all other spins. So, that each spin feels a magnetic field like this, and say there is also an external magnetic field, and we can combine them and write down a one particle equation or one spin equation in an effective magnetic field given by this term, okay, this term, and so on, where these m is nothing but the average value of this spin, that is Si plus delta, and Z denotes of course the coordination number. So, in 1D the coordination number is 2, in 2D it is 4, and so on. Again we take a statistical root and we can calculate the partition function. Now, it became a one particle problem or a one spin problem, that one spin. So, you go to any spin and consider the effect of all other spins due to that is as if the spin is an effective field, and we also have an external field, but this effective field due to all other spins modifies or renormalizes the external field, and we get this everything in terms of this B effective. And again we get a Brillouin function as we have seen there. So, by taking this del f del B effective, we know the partition function. So, we can get f by taking a kT log z, and then we can get this magnetization, which has this form in terms of the Brillouin function. So, in the limit this h going to 0, one can actually take this expansion of this Brillouin function, and very similar to what we have done. So, the magnetization really looks like this, and we can extract out the transition temperature, which is Tc equal to S into S plus 1 by 3 into Zj. Z is the coordination number, and what we get is this, that the m versus temperature, that means as you are increasing temperature, initially this magnetic ordering, it is resilient to temperature. So, it sort of is slow here, it kind of kind of flattish here, but as you keep increasing the temperature, the thermal these effects or the thermal energy will randomize the the alignment of the spins, and you will keep getting these magnetic moment or the magnetization destroyed, and it will go to 0 at T goes to Tc. And this behavior is important, that close to T equal to Tc, this goes as 1 minus T by Tc to the power half, and this is the hallmark of mean field theory being put in action, is basically this T to the power half or 1 minus T by Tc to the power half is the feature for this magnetization or the behavior of magnetization. And at T equal to 0, it has a value which is gamma s, and that is all these things are mentioned here, and so on. gamma is equal to G, the Landé factor into the Bohr magneton. So, that is all what we do for magnetism. It is a very brief discussion of magnetism, but I hope that you got a feel that what these different magnetic orderings are, and that the diamagnetism and the paramagnetism are still treatable within independent electron approximation, which is what we have done. We have started from the kinetic energy term, modified the momentum to P minus E A, and have done these calculations. We got these QD susceptibility for the paramagnets, and we also got a diamagnetic susceptibility, these we have done it for diamagnetic susceptibilities for the insulators, and the ones that are partially filled systems which have some metallic properties, they are characterized by the this QD susceptibility, but then we have also distinguished it with another kind of susceptibility, which is the Pauli susceptibility. And then we have done an elementary treatise of ferromagnetism, where there are spins that are arranged, and we are not talking about the dimension, because as soon as you do a mean field theory, the dimensional information goes away, and it only sort of enters through the number of coordination, the coordination number Z, or the number of nearest neighbors. And we found that the magnetization of the system as a function of temperature, it falls off like this, that is shown on your screen, and the characteristic behavior as T goes to T c is 1 minus T by T c to the power half. Okay. We will stop here. Thank you.